Okay, 2.5 is on physical applications. Of integration. And I'll just say a caveat here. This is in no way supposed to be an exhaustive covering of the topic. There are an infinite number of physical applications of integration. This is just a smattering of certain applications of integration. And these are just the kind of some basic ones that we're going to cover. But this is in no way, shape, or form to be an exhaustive or something that's going to cover all of the physical applications of integration. Now, we would be here forever. So, and most of the physical applications of integration will occur in your physics classes and engineering classes. So, we have a ton of physical applications of integration. So I'm just going to show you a few. Okay. Okay, let's start with mass and density. Okay, so P of X is referred to as the density function. In some texts, you'll see it as rho, a Greek letter rho. But rho looks really close to P, so we'll just go with P. Okay, density, P of X, is the measure of the ratio mass to volume. Okay, that is density equals M over V. If density varies within an object, and is modeled as P of X, then the mass can be found using an integral. Okay, where the mass is equal to the integral a to b of the density of x dx. So this is synonymous Is there another y there? I think that's good. Okay, synonymous to m equals dv. So we're kind of taking the density over this volume, and we're integrating the density function over over an area, and it gives us the mass. Okay, number one. Consider a thin rod oriented on the x-axis over the interval pi/2 to pi if the density of the rod is given by P of x equaling sine of x kilograms per meter cubed. Okay, then what is the total mass of the rod? Okay. We have this rod that has a varying density, but it's oriented on the x-axis. Okay. From pi/2 to pi. Okay. So we're going to take and solve for the mass. Okay. And so this is pi/2 to pi of sine x dx. This is going to get me, so the mass is equal to this guy, which is going to get me negative cosine x from pi/2 to pi. Remember, all sine is negative cosine. And so now we plug in our limits of integration, we get negative cosine of pi minus negative cosine of pi/2. Well, the cosine of pi is -1, so this becomes the negative of a -1. The cosine of pi/2 is 0, so this whole thing goes to 0. So this is just plus 0. And so this becomes 1. And the mass was given to us in kilograms, because the density was kilograms per meters cubed. And so it's just 1 kilogram. The whole rod has a mass of 1 kilogram. Okay, how do we find the mass of a disk? The mass of a disk, it wasn't a rod, but it was a disk. That guy would be 0 to r. R is the radius of the disk. How far out it goes. 2 pi x times the density P of x dx. Okay, where r is the radius of the disk. Okay, so we have a way to figure out densities of rods and disks where the mass of rods and disks where the density varies. Number 2. Let P of x equal the square root of x kilograms over meters cubed represent the radial density of a disk. Calculate the mass of the disk with radius 4 meters. Radius of 4 meters. So the mass is going to be 0 to 4 of 2 pi x times p of x, but p of x was the square root of x dx. So this is equal to 0 to 4. I'll pull the 2 pi out in front. This is x times x to the 1/2. Dx. Combining those, I get x to the 3/2. From 0 to 4, 2 pi out in front, dx. Okay, let's integrate. This goes up to 5/2, so I multiply by my reciprocal 2/5, x to the 5/2 from 0 to 4, with a nice 2 pi out in front. Okay, plug in 4 and 0, we get 2/5 times 4 to the 5/2 minus 2/5 times 0 to the 5/2 times 2 pi. Okay, so this thing obviously goes to 0. And 4 to the 5 over 2. Okay, we can rewrite that as 2/5 times the square root of 4 to the 5th power times 2 pi. Okay, so that guy is going to be the square root of 4 is 2. 2 to the 5th power is 32. So that's going to be 32 times 2, which is 64, times 2, which is 128. And that is in kilograms. Because once again, we're finding the mass. Okay. Let me go back. You need to catch up with the writing. Okay, work. Let's talk about work. Okay, work equals force over distance. We can think of it in terms of Newton's second law of motion, F equals ma, but this is mass times acceleration times distance. Okay, that's if everything is nice and linear. We're going to need to use some integration when it's not linear to integrate the distance. Okay, the mass and acceleration, that should remain constant, but the distance may not, and the volume may not. So the spatial relations of our object is what's varying. Okay, a couple of things that we should note. Force due to gravity is called weight. And weight equals mg, where g is the acceleration of gravity. And SI units, mass is in kilograms, and G is 9.8, roughly 9.8 meters per second squared. Okay, so weight is equal to mg is in kilogram meters per second squared, which we call a Newton. Okay. Not to be confused with those very yummy cookies. Okay. Distance is in meters. And so work equals force over distance, which is kilogram meters squared over seconds squared, which is called a Newton meter, or a joule. Okay, so work is going to be in joules. Okay. In imperial units, okay, like in the United States, because we like to be different than everybody else. Okay, mass is in pounds mass. Okay, and it's not really used on Earth. It's not used on Earth because acceleration and gravity doesn't change on Earth, and unless we were to go to the moon and do all these calculations again on the moon, we wouldn't really need to change them. If we honestly went to the moon, we would probably just use SI units anyway, because they're easier. Okay, mass is in pounds mass. Okay, G is equal to 32 feet per second per second. Okay, weight is really what we talk about when we say, hey, how much do you weigh? Okay, that's we're talking about how much do you weigh here on Earth. That's mg, and that's in just pounds. Okay, or LBS for short. You could think of it as pounds force if you want. Okay, but nobody says, hey, how many pounds force are you today? And I'm like, well, I'm 185 pounds force. No, you just say I'm 185 pounds because we're all referencing living on this planet. Okay, distance is in feet. Okay, so work is in pounds times feet, or what we call foot pounds. Okay, and what's interesting is that 1 foot pound is approximately 1.36 joules. So they roughly have, you know, within a factor of 10, they're roughly the same, you know, amount of work done. Okay. Just like how a mile and a kilometer are, you know, within a factor of 10. Okay, within the same, I think 1 to 1.5 or something like that. Okay, joules and foot-pounds can be converted kind of nicely back and forth as well. Okay. Sometimes mass is unavailable but density and volume are given. So we can solve for the mass using D equals M over V or M equals dV. Okay, we need calculus, particularly integration. Okay, if the force varies, the force being applied varies, the distance varies, okay, or they both vary. Okay, so work is equal to the integral from A to B of the force function over the distance. Okay, and we get work is equal to the integral A to B of f of x dx. Okay, force over distance. Okay, Hooke's law. Okay, Hooke's law states that force required to maintain a spring stretched x units beyond its natural length is proportional to x. Okay, the distance that it is being stretched. Okay, so the force of x is equal to some proportionality constant times x, where k is called the spring constant. Okay. Number 3. A force of 40 newtons is required to hold a spring that has been stretched from its natural length of 10 centimeters to a new length of 15 centimeters. Okay. How much work is done in this stretch? Okay, so we know that basically 40 newtons is required to stretch this thing 5 centimeters. Okay. So the force required, Kx, is equal to 40. Whereas x is equal to 0.15 centimeters, oops, 0.15 meters, I should say, minus 0.10 meters is equal to 0.05 meters. Okay. So it's 0.005 meters of stretch. So how can I figure out what K is? Well, K times 0.05 is equal to 40. So the force is linearly proportional to the distance. Divide by 0.05 and I get K to be equal to 800. So the force of the spring is going to be equal to 800 times the distance stretched. Okay. So if we had a, like a little diagram here, it would look like this. We'd have this spring, its natural length is 10 centimeters. When we stretch it, it goes to 15 centimeters, which is an extra 5 centimeters of stretch. Okay, so we want to find the work done. Well, the work is going to go from A to B of f of x dx, okay? So what are my limits of integration? What am I going from?
0.10 meters to 0.15 meters?
No, because it says back here, it says the force required to maintain x units beyond its natural length. X units beyond its natural length. X was going from rest, right? There's no force involved in letting a spring just be at rest. I didn't have to force it to 10, and now I'm forcing it to 15. Does that make sense?
I see.
Is it 0 to 0.05 meters?
Exactly. Yeah, thank you, Machiavelli. It is 0 to 0.05 because when it's at rest at 10, there's no force involved. So it's zero distance. So this is equal to 0 to 0.05 of 800x dx. Okay, I'm gonna make this 800x squared over 2 from 0 to 0.05. This is 400 times 0.05 squared, okay, minus the 400 times 0 squared, but that's gonna go to 0. Okay, and if I plug this into a calculator, I get 1. This is exactly 1 joule of work. Okay, exactly 1 joule of work. Okay, 1 Newton meter. Okay. I'm going to tell you right now one of the problems that are on the exam. You have 8 problems on the exam. The next example will be very similar to one that's on it. Okay, so this next example you're going to want to study, because one of the problems on the exam is very similar to it. I'll just give that to you at this point. A tank has a shape of an inverted circular cone with a height of 10 meters and a base radius of 4 meters. It is filled to a with water, I should say, to a height of 8 meters. Find the work required to empty the tank by pumping all of the water to the top of the tank. And I'll give you a minute to finish writing that down. But the distance required to pump the water is constantly changing. That's why we have to use calculus. Okay. Okay, let's draw a picture of an inverted circular cone with dimensions of 10 by 4. This is 4, okay, meters. This is 10 meters. Okay. we have water in the tank up to the 8-meter line. Hmm. So far, so good. At the 8-meter line, how far does the water have to travel to get over the edge? If I pump the water up and over, okay, assuming that we're not traveling any distance laterally, we're just going up and out, up and out. Okay, as soon as it reaches the top of the cylinder, it's out. Okay, there's a big spigot right here at the very top. Okay, once it reaches that spigot, we can collect it. Right?
Two.
2, yeah, thank you, Macchiali. Yeah, 2. But what happens as we take more water out? What happens as we take more and more water out? What happens to the water level?
It decreases.
It decreases, which makes the distance I have to travel do what?
Go up.
Increase. Right? So it will, so think of each water molecule as a particle that needs to be lifted out of the tank. We're going to change that a tiny bit, but think of each water molecule as a particle that needs to be lifted out of the tank. Okay. But is shaped like an infinitely thin disk of water. Right? Infinitely thin disk of water. So what does that mean? It means that every second we're pulling water out, we can think of it as one molecule as an infinitely thin disk of water that we're pulling out. Okay, this would be my infinitely thin disk of water that we're pulling out. We're pulling out these infinitely thin disks. Okay, infinitely small disks, we're just doing it infinitely fast, and we eventually get all the water out of the tank. Okay. Let x equal the distance to the top of the tank for any given particle. Okay. Think of any single sheet of water as a disk of area pi r squared and a thickness of delta x. Okay, so this disk here has a volume of pi r squared delta x. Okay, then x. Okay, we're going to sum up all of these values of x. Okay, for our distance. Okay. Okay, we're gonna have to eventually go from 2 to 10 because we're gonna have discs that are 2 meters away from the spigot, and we're gonna have discs that are 10 meters away from the spigot at the very end. So 2 at the start, 10 at the end, but everything in between. So the volume of those discs are gonna be moving up. Okay, where the thickness of those discs are delta x. We're going to let the limit of delta x go to 0, but we still have to account for adding all of them up, adding all of those infinite discs up and getting them out of the tank. Okay. So the volume of any single disk, we'll say any single sheet, is V equals pi r squared delta. Don't forget the delta x. Okay, that's gonna be very important. When we plug this into an integral, that's going to become an x. Okay. Okay, because it's part of the volume. It's part of the volume. It's not part of the force or the distance. It is a thin distance, and we just have to sum it all up, all of them up from 2 to 10. Okay, all these disks. Okay. Okay, one thing that we need to know, okay, is that the volume, or so I should say the density of water, okay, is 1 gram per cubic centimeter. Which is equivalent, we're going to change this to 1,000 kilograms per cubic meter. Okay, so 1,000 kilograms per cubic meter. So we just did the unit conversion there in SI units. Okay. From similar triangles, okay, we get what? Let's look at this. So I want R, I'm going to put this in black. Okay, we want R to what? Okay, R to what is this distance here? Okay, if the whole thing is Okay, if the. Let's get rid of the H right now. Bring it back here. Okay, what is the height of the water at any given time? Okay, we're gonna call this guy R. Okay, and then I want to actually use this guy over here. Because remember, X is the distance that I have to that I have to go back up. Okay, so X is this distance that I have to travel up. Okay, and so to use similar triangles, okay, I want to use 4 to 10. Okay. Let's go 4 to 10 is equal to, so similar triangles. What triangles? Let me highlight the triangles that we're looking at. Looking at this triangle. Okay, and then this triangle here. So we've got to relate 4 to 10 to, okay, I am going to get rid of the H right now. Okay, so 4 to 10. Okay, and so then what's this piece down here? Well, that's if X is the distance that I have to travel back up, then 10 minus X is the height of the water at any point. Okay, 10 minus X is the height of the water at any point. That's that guy there. So we'd say 4 to 10 is a similar triangle as R is to 10 minus X. Okay. Okay, so 4 to 10 is similar to R over 10 minus X. Okay, solving for R, okay, you can multiply both sides by 10 minus X. Okay, we get 4/10, which reduces to 2/5 times 10 minus X. Okay, and that's what the radius is at any point. Okay, in terms of the height. Okay, using similar triangles. Okay, why is this important? Because we need to figure out the work. Okay, the force over the distance here. Okay. What's the work? The work is equal to an integral of force over distance. Right? Force over distance. Okay. Force over distance. Okay. Okay. So the idea is we need to figure out, well, the expression for the force. Okay. So we don't have the mass, which would be nice, but we do have the density and the volume. Okay, of water. Now the volume of the water is constantly changing. Okay, but we do have an expression for the volume. The volume, once again, was oops, this is wrong. I don't know what I'm doing. The mass is D times V, I'm sorry. dV, not D over it. Okay, so the volume was equal to, remember, it was pi r squared delta x, right? But now we have an expression of R in terms of X. Okay, so we're going to plug that in here. We say, oh, okay. The volume is equal to pi times Okay. 2/5 times 10 minus x squared, okay, delta x. Okay. So we now know the m, or the mass. What we really want is the force, which is mg. The force is mg, okay. So we can take the volume, plug in for the volume, multiply it times the density of water, and then multiply that times the acceleration due to gravity. We should get a function for the force. Okay, so force should be equal to, okay, the mass, which is d times v times g. So d, I'll just put dgv, okay, since v is the variable. So the density of water was 1,000 kilograms per meter cubed. The acceleration due to the acceleration due to gravity is 9.8 meters per second squared. And then the volume here is going to be this pi times, I'm going to square this out. This is 4/25 times 10 minus x squared delta x. Okay, so that's a force. That's my force function. That's my f of x. Okay. Now, what happens when I plug this thing into the integral? Okay, what are we integrating over? Well, it's the distance that we have to start with and the distance that we're stopping at. So what's the distance that we're starting at when we have the tank at 8 meters? Okay, when the tank is full at 8 meters, the distance is that we have to travel is 2 meters. That guy's 2 meters. That when the tank is empty, just before it's empty, that very last infinite sheet had to have traveled all the way up the tank and at 10 meters. Okay. Okay, when I bring this inside, this delta x, it becomes an x. Okay, because I've got to sum all of those delta x's from 2 to 10. So this becomes an x. Okay. Let me get rid of this. This is the work done is from 2 to 10 of 1,000 times 9.8 times 4 pi over 25 times 10 minus x squared times x dx. Oh. Easy, right? Okay, let's reconcile some of these constants here. If we were to multiply that all together, I would end up with 1568 pi. So this equals 1568 pi. Right? Integrate from 2 to 10 of 10 minus x squared times x. So this delta x becomes an x. And The reason it becomes an X is because it's really not area, it's volume. So we do have to take into account that we have a third dimension. Okay. So now we just need to do the calculus. Okay, so and, it shouldn't be too difficult. Okay, so we're just going to multiply all of this out. This is equal to 1568 pi. 2 to 10, this is going to be 100 minus 2x plus x squared times x dx. I'm sorry, this is not 2, this is 20. Okay, let's distribute the x. So this becomes 1568 pi 2 to 10 of 100x minus 20x squared plus x cubed dx equals 1568 pi. Okay. Now let's integrate. This is going to be 100x squared over 2 minus 20x cubed over 3 plus x to the 4th over 4. Evaluated from 2 to 10. Okay, this is now just becomes kind of a numerical problem. This becomes 50 times 10 squared minus 20 times 10 cubed over 3 plus 10 to the 4th over 4 minus 52 squared minus 20 thirds 2 cubed plus 2 to the 4th over 4. Okay, now we just have fun with fractions. Okay, 50 times 100 is 5,000. This becomes 2,000, no, this becomes 20,000 over 3. This becomes 10 to the 4th, which is 10,000. Divided by 4 is 2,500. This is 50 times 4, which is 200. This is 8 times 20, which is 160 over 3. And then this is 2 to the 4th, which is 16 over 4, which is just 4. Distribute, maybe combining some like terms in the process. Okay, let's see. So we can combine these guys, we can combine these guys, right? So this is going to become 7,500 minus 20,000 over 3 minus 204 plus 160 over 3. I can get rid of the brackets. This is equal to 1568 pi. Okay. So now 7,500 minus 204 is 7,296. This is going to be 20,000 minus 160, which is 19,840 over 3. 1568 pi. Okay. Finding a common denominator of 3, this becomes 21,888 over 3 minus 19,840 over 3 times 1568 pi. Okay, this becomes 2048 over 3. $2,048 over 3, which is then equal to 3,211,264 over 3 pi. I could put the pi on top of this. I don't know. It doesn't matter. Pi joules. Okay. Which is approximately 3,362,827.8 joules of work done. Okay. Okay, and that is 2.5.